In August of 2025, a mountainside in a remote fjord in southeast Alaska gave way, and what happened next was almost incomprehensible. Computer simulations built from the actual field data show the resulting tsunami produced a breaking wave roughly 330 feet high, as tall as the new World Trade Center tower, racing across the water at more than 150 miles per hour when it struck the opposite shore. Nobody saw it coming in real time, but scientists studying the seismic data afterward found something they weren't expecting. The hillside had been sending out warning signals for nearly 24 hours before it finally failed. That discovery is now driving a broader, ongoing effort to catch the next one before it happens. And the signals researchers are learning to read are stranger and more specific than almost anyone expected. The event itself struck at Tracy Arm, a narrow glacier-carved fjord in southeast Alaska. According to the Alaska Earthquake Center, the landslide was preceded by the rapid retreat of a glacier that had been physically supporting the slope above it, a common and increasingly frequent pattern across the region as warming temperatures accelerate glacial melt. As that supporting ice thinned and pulled back, the rock face it had been buttressing lost the structural support that had likely held it in place for a very long time. When it finally gave way, an enormous volume of rock and debris slammed into the fjord's waters below, displacing enough water to generate a wave of genuinely historic scale. Research seismologist Ezgi Karasozen at the Alaska Earthquake Center described the scale of what happened in blunt terms, calling what's unfolding across Alaska unprecedented. Here's the detail that turned this from a singular disaster story into an ongoing research effort. When scientists went back through the seismic recordings from monitoring stations in the region, they found localized seismic signals that began days before the slide, and more specifically, sharp seismic popping sounds, detected for almost 24 hours, leading up to the collapse itself. Michael West, a researcher involved in studying the event, described those signals in a striking way, comparing them to the hillside essentially announcing its own failure in advance. The scientific team studying Tracy Arm has framed their findings as something between a discovery and a warning. Alaska has sophisticated, well-established systems for monitoring earthquakes and separate observatories dedicated to tracking volcanic activity. But this massive, genuinely dangerous landslide occurred without any dedicated monitoring system in place to catch it, and researchers are now explicit that this represents a hazard Alaska needs to directly confront rather than treat as an isolated one-time event. That gap is exactly what a separate, ongoing research project in a different part of Alaska has been working to close, and its findings, published in December of 2025 in the journal Seismological Research Letters, add a genuinely important new piece to this picture. Since 2020, researchers led by Gabrielle Davy at the University of Alaska Fairbanks have maintained a dedicated monitoring network around the Barry Landslide, a large, actively moving slope in Prince William Sound that scientists have identified as carrying serious tsunami potential of its own if it were to fail suddenly. Unlike Tracy Arm, where the danger only became fully apparent after the fact, Barry Landslide has been under direct, continuous seismic surveillance for years, specifically because researchers already understood its hazard potential and wanted to catch warning signs before any failure, not after one. What they found while analyzing years of continuous seismic data was something nobody had specifically identified before, a distinct, previously unrecognized category of seismic signal. These are sharp, high-frequency pulses that become measurably more common starting in late summer, continuing through the middle of winter, and then abruptly stop in late winter or early spring. A clear, repeating seasonal pattern rather than random background noise. The research team's leading explanation is that these signals are being generated by water freezing and thawing within cracks in the rock itself. As water seeps into fractures in the slope and then freezes, it expands, exerting mechanical stress on the surrounding rock, stress capable of producing exactly the kind of sharp, high-frequency seismic pulse the monitoring instruments picked up. As that ice eventually thaws and the pressure releases, the signal pattern changes accordingly, tracking the seasonal freeze-thaw cycle closely enough that researchers could identify it as a distinct, physically explainable phenomenon, rather than dismissing it as unexplained noise in the data. To help verify what was actually producing these signals, researchers set up GPS time-stamped cameras positioned above Barry Glacier back in 2020, and time-lapse footage from those cameras helped directly tie specific seismic signals to real, observable motion happening on the glacier and across the Barry Arm landslide slope itself. That combination, continuous seismic monitoring paired with visual confirmation from time-lapse imagery, is what allowed researchers to move from simply detecting an unusual signal to actually understanding the physical process generating it. Here's why this specific discovery matters well beyond simply explaining an odd seasonal pattern in the data. Water repeatedly freezing and thawing within rock fractures is a genuinely destructive process over time, a mechanism geologists call frost wedging, where repeated freeze-thaw cycles gradually widen existing cracks and weaken the overall structural integrity of a rock face. If these newly identified seasonal seismic pulses are directly tracking that exact process in real time, they could eventually function as a meaningful early indicator of how a landslide-prone slope's structural stability is changing year over year. Not necessarily predicting a specific date of failure, but tracking the gradual weakening that precedes one. Researchers have described this as a potentially important clue, worth continued monitoring rather than a definitive predictive tool on its own. An honest, appropriately cautious way to characterize a genuinely new finding, still being actively studied. It helps to understand why a landslide-generated tsunami behaves so differently from the more familiar earthquake-generated tsunami most people picture. An earthquake tsunami typically forms when a fault ruptures across a broad stretch of ocean floor, displacing a huge area of water gradually and generating a wave that, while capable of traveling across an entire ocean basin, usually arrives at a distant shore as a rising surge rather than a single towering wall of water. A landslide tsunami works through a completely different, far more violent mechanism, an enormous mass of rock and debris slamming into a body of water essentially all at once, displacing water almost instantaneously at the exact point of impact. In a narrow, enclosed fjord like Tracy Arm, that displaced water has nowhere to spread out and dissipate the way it would in open ocean, it gets funneled directly across the confined waterway, which is exactly why a landslide tsunami in a setting like this can produce a wave hundreds of feet high near its source, far taller than almost any earthquake-generated tsunami, even though the total energy released may be considerably smaller than a major undersea earthquake. Alaska has direct, well-documented historical experience with exactly this kind of event, and it remains one of the most extreme examples ever recorded anywhere on the planet. In July of 1958, an earthquake along the Fairweather Fault triggered a massive rock slide into Lituya Bay, another narrow, glacially carved inlet in southeast Alaska, generating a wave that stripped trees and soil from surrounding slopes up to a documented 1,720 feet above sea level, the tallest wave run-up ever scientifically recorded anywhere in the world. That event happened decades before the kind of continuous seismic monitoring networks now being deployed around sites like Barry Landslide existed anywhere in the region. Lituya Bay stands as the clearest possible demonstration that southeast Alaska's combination of steep, glacially oversteepened slopes and narrow enclosed waterways creates genuinely unique conditions for producing landslide tsunamis of an extraordinary scale. Conditions that current research suggests are becoming more common, not less, as the region continues to warm. If a story like this is the kind of thing that makes you think differently about hazards hiding in plain sight, that's exactly why this channel exists. Now, here's why Alaska specifically has become such an urgent focus for this kind of research, and why scientists expect this problem to keep growing, rather than staying contained to a handful of known landslide sites. Alaska's coastal and fjord landscape is shaped almost entirely by glaciers, both the ones actively present today and the deep erosional work done by much larger glaciers during past ice ages. Many of Alaska's steep coastal slopes have spent thousands of years with a glacier physically pressed against their base, providing constant structural support the way a retaining wall holds back a hillside. As warming temperatures accelerate glacial retreat across the region, that support is being removed from an increasing number of slopes simultaneously, all at a historically unprecedented pace. Separately, permafrost, permanently frozen ground that has helped hold soil and rock together across much of Alaska for millennia, is also degrading as temperatures rise, removing a second, independent source of structural stability from many of the same slopes. Researchers studying the Tracy Arm event have been explicit that the likelihood of similar large-scale landslide events has increased substantially across Alaska's north as a direct result of these two compounding processes: retreating glaciers and thawing permafrost working together to destabilize slopes that had remained physically stable for a very long time. The practical stakes here extend well beyond the immediate landslide sites themselves. Alaska's fjords and coastal waterways are a major destination for the cruise ship industry, carrying large numbers of passengers directly through narrow waterways that sit close to exactly the kind of steep, glacially supported slopes now becoming increasingly unstable. Researchers studying these events have specifically called on coastal municipalities, the cruise industry, and other regional stakeholders to take this evolving threat seriously, given how little warning a sudden landslide-generated tsunami can provide in a narrow fjord, where a wave doesn't have to travel far or long before reaching inhabited shoreline or a passing vessel. It's worth being precise about what monitoring systems like the one at Barry Landslide can and can't currently promise. Even Michael West, closely involved in studying these seismic warning signals, has been careful to note that not every landslide produces this kind of detectable seismic activity beforehand, meaning a monitoring network built around these signals won't catch every future event with certainty. But where these signals are present and can be reliably read, researchers believe they could provide what West described as precious seconds of additional warning time, potentially enough to alert nearby communities or vessels before a wave arrives. In a narrow fjord environment, where a landslide-generated tsunami can strike the opposite shore within minutes of the initial collapse, even a modest amount of additional warning time represents a genuinely meaningful, potentially life-saving improvement over having no warning system in place at all, which was precisely the situation at Tracy Arm. New seismic monitoring equipment installed in the region since the Tracy Arm event has already demonstrated a concrete, practical improvement, enabling researchers to identify a subsequent slide rapidly, a process that previously could have taken days to confirm using older monitoring infrastructure. That improvement in detection speed alone represents genuine progress, even before accounting for the added value of potentially recognizing pre-failure warning signals like the ones identified at Barry Landslide. There's also a broader scientific value in treating the Tracy Arm event as a natural experiment rather than simply a disaster to move past. Because researchers were able to gather such detailed field data from an event of this specific scale and mechanism, an actual landslide of this size striking water and generating a tsunami, with this precise a set of measurements, it gives the tsunami modelers genuinely rare, high-quality data to refine their simulations for similar potential events elsewhere in the world. Karasozin has noted directly that events with this combination of scale and available data are genuinely uncommon for researchers to study, making the resulting data set valuable well beyond Alaska's own coastline, informing how scientists model landslide-generated tsunami risk in other glacially influenced coastal regions globally, from Norway's fjords to similar terrain elsewhere in the Pacific Northwest. This growing concern is part of a much broader pattern of seismic and tsunami hazard research happening across Alaska right now, not an isolated focus on just these two sites. According to the United States Geological Survey, Alaska experiences more large earthquakes than the rest of the United States combined, and more than 3/4 of the state's population lives in an area capable of experiencing a magnitude 7 earthquake. The USGS Alaska Earthquake and Tsunami Hazards Team conducts ongoing field research specifically examining how, where, and why earthquakes and tsunamis occur across the state, including dedicated work characterizing active fault systems like the Queen Charlotte Fairweather System, the same general fault zone responsible for the historic 1958 Lituya Bay event, and separate studies mapping tsunami hazard zones in populated areas like Upper Cook Inlet near Anchorage. Researchers have even deployed seismographs directly on lake beds in certain areas, alongside networks of land-based instruments, specifically to build more complete, three-dimensional pictures of how seismic energy moves through this genuinely complex landscape of fjords, fault systems, and rapidly changing glacial terrain. That broader context matters because it shows the Barry Landslide Monitoring Project, and the lessons learned from Tracy Arm aren't standing alone. They're part of a coordinated, expanding effort to close monitoring gaps across a state where the underlying geology, retreating glaciers, thawing permafrost, and active fault systems, keeps generating new hazards faster than monitoring infrastructure has historically been able to keep pace with. The 2018 magnitude 7.1 earthquake that struck near Anchorage and the 1964 Great Alaska earthquake before it remain two of the most significant, well-studied seismic events in Alaska's modern record, and both continue to inform how researchers think about risk and monitoring priorities across the state today. Adding a new, previously unrecognized category of seismic signal, one tied specifically to freeze-thaw weathering rather than tectonic stress, gives this broader research effort a genuinely new tool, one aimed at the specific, accelerating hazard of glacially supported slopes losing their stability as Alaska's climate continues to change. There's also a genuine feedback dynamic worth understanding here, because it explains why researchers describe this as an accelerating problem rather than a stable, predictable one. As glaciers retreat and expose more previously ice-covered rock to the atmosphere, that newly exposed rock becomes immediately subject to the same freeze-thaw weathering process identified at Barry Landslide, meaning the total area of slope, vulnerable to this specific destabilization mechanism, keeps expanding as warming continues. At the same time, permafrost degradation is happening across a much broader footprint than any single monitored landslide site, meaning researchers can't simply install sensors at every currently known unstable slope and consider the problem solved. New areas of concern are likely to emerge as previously stable terrain loses the ice and frozen ground that had held it together for centuries. This is part of why the research community studying these hazards has emphasized expanding monitoring capacity as a genuine priority, rather than treating Barry Landslide and Tracy Arm as two isolated, fully understood cases. Every additional year of continuous seismic data collected at monitored sites, adds to a growing baseline understanding of exactly what a slope's seismic signature looks like as it moves from stable to weakening to genuinely hazardous, knowledge that becomes more valuable specifically because it can eventually be applied to interpreting signals from newly identified at-risk slopes elsewhere in the region, without requiring years of dedicated monitoring at each new site before that data becomes useful. So here's where this leaves things. A remote Alaskan fjord produced one of the largest landslide-generated tsunamis on record in 2025. And in studying exactly what happened, researchers found the mountainside had been giving off detectable warning signals for nearly a full day beforehand. That discovery, combined with a separate multi-year research effort identifying an entirely new category of seasonal seismic signal tied to freeze-thaw weathering at a different, actively monitored landslide site, is beginning to build the foundation for genuine early warning capability in a region where, until very recently, this specific hazard had gone essentially unmonitored. As Alaska's glaciers continue retreating and its permafrost continues thawing, researchers expect this to remain an active, evolving area of study, not a problem with a clean, finished solution. We'll continue tracking how this research develops as scientists refine their understanding of these seismic precursor signals. Thank you for watching, and I'll see you in the next one.